So now we're on to question 2 of our 2018 maths paper. So we're told that a curve C has this equation here, x squared minus 2x minus 24 root x, for x is greater than 0. And in part A, we first want to find dy over dx. So it might just be helpful to rewrite our equation here as y equals x squared minus 2x minus 24x to the power of a half. That way we can just clearly see what the exponent is, and it might make it easier when we differentiate each term. So let's go ahead and do that. We want dy over dx. So if we differentiate it term by term, so x squared differentiates to 2x. So we're just bringing down the power in front and then minusing 1. So we get 2x. And then if we differentiate minus 2x, we just get a constant value of minus 2. So it's just the coefficient value. And then if we differentiate minus 24x to the power of a half, we're bringing down a factor of a half, multiplying it by the coefficient of x to the half, and then we're taking away 1 from the exponent. So what we're doing is we're writing minus 24, that remains, the coefficient remains, and then we're multiplying by a half, because we have a half in the power, and then we have x to the power of a half minus 1. So let's rewrite that. 2x minus 2 minus 12x to the power of minus a half. And now we've done it. Okay, so now part I, we want the second derivative of our curve equation here. So it follows on quite well from part I, because all we need to do is we need to differentiate for a second time our function y, but we've already differentiated the first time. So let's just differentiate the first derivative. Yeah, so if we do that, then we're looking at each term here in our dy over dx expression. So then d squared y over dx squared equals, again, differentiating term by term, 2x differentiates to 2. We just have the constant coefficient remaining. Minus 2 differentiates to nothing. So any constant value, when you differentiate it, you get 0. So then all that remains is for us to differentiate minus 12x to the power of minus a half. So we're doing the same thing again. Let's bring down a factor of that power, multiplied by the coefficient, and then minus 1 from minus 1 in the exponent. So writing that out, we have minus 12, that remains, and then we're multiplying by the value in the exponent, so that's minus a half, x minus a half minus 1, so that's equal to 2 minus 12 times minus a half, that's plus 6, x minus a half minus 1, that's minus 3 over 2. So now we have our d squared y over dx squared expression as well. Okay, so that's part A done. Now in part B, we're asked to verify that C has a stationary point when x equals 4. So that's part B. So we know that at a stationary point, dy over dx equals 0. So what we're trying to check and what we're trying to verify here is that when x equals 4, if it is a stationary point, dy over dx should equal 0. So let's have a go at doing that. Let's substitute in x equals 4 into our expression for dy over dx. If we get 0, then we can confirm that there is a stationary point at x equals 4. So dy over dx equals 2 lots of, so we're substituting in x equals 4 here, so 2 lots of 4 minus 2 minus 12, 4 to the power of minus a half. So that comes from this term here. So let's multiply that out. So 2 times 4, that's 8, minus 2, minus 12. Now 4 to the power of minus a half, you can rewrite that a bit to help you. That's over 4 square rooted. Okay, that's our power of a half. So we can rewrite 4 to the minus a half as 1 over 4 to the half, which is 1 over root 4. Okay, so what's that going to equal? That's 8 minus 2 minus 12 over 2. That's 8 minus 2 minus 6, which is 8 minus 8, which is 0. So when x equals 4, dy over dx is in fact 0. And so we verified that when x equals 4, there is a stationary point. So now for part C, you want to determine the nature of this stationary point, and you want to give a reason for your answer. So let's try and remember how we determine the nature of a stationary point. So the easiest way for us to do that is to look at the second derivative here. So for a stationary point, if d squared y over dx squared is less than 0, we have a maximum point. And if d squared y over dx squared is greater than 0, then we have a minimum point. We could also have the case that d squared y over dx squared is equal to 0. And if we have that, then it's neither a maximum nor a minimum point, and we have to investigate the points around it. So if we have a look at our example here, what is d squared y over dx squared? It's this expression here. So what we're going to do to determine the nature of our x equals 4 point, we can just plug in x equals 4 into our expression for d squared y over dx squared. So let's do that. Let me rewrite d squared y over dx squared here. So that's 2 plus 6x to the minus 3 over 2. 3 over 2. 4x equals 4. D squared y over dx squared equals 2 plus 6, plugging in x equals 4 to the power of minus 3 over 2. And let's think about how we rewrite this here to help us calculate it. So 4 to the minus 3 over 2, we can just write that as 1 over 4 to the 3 over 2, which can be written as follows. So we're rooting it and cubing it. And to get rid of the negative sign in the exponent, we work out the reciprocal. So we write it as the reciprocal there. So what's that going to be? that is actually equal to 1 over 2 cubed, which is 1 over 8. Okay, so that's equal to 2 plus 6, 1 over 2 cubed. We can already see that this is going to be greater than 0, so we can just work it out anyway. 6 over 6 times 1 over 8, which is 2 plus 6 over 8, which is 2 plus 6 over 8 we can simplify to 3 over 4. So we can kind of keep that as a mixed fraction here, 2 3/4. Clearly d squared y over dx squared is greater than 0, hence we have a minimum stationary point.